Swayam Prabha. Digital India. Educated India.
Welcome back to this NPTEL course on Muffler Acoustics. So, we are in week 11 and for the first time we will be doing the 3-dimensional analysis of rectangular chamber mufflers as well as circular cylindrical mufflers in this lecture. So, this is here week 11 and what we have today is lectures 2 and 3 combined of week 11. So, what we are going to do exactly in this lecture is that we will present a proper theoretical formulation of how to characterize different single inlet and single outlet rectangular chamber mufflers as well as circular cylindrical mufflers with arbitrary location of ports. Although this formulation, like I mentioned in the last class, can be used to analyze system with multiple ports, I mean more than 2 ports, I mean to say, like single inlet and double outlet or single inlet and triple outlet or 2 inlets and 1 outlet and different combinations, but we will restrict our discussion to single inlet and single outlet system or CISO system. So, we essentially have a 2 port system, 2 port rectangular chamber or a circular cylindrical chamber. So, let us start with your basic equations that govern wave propagation. For simplicity, what we will do is that we will consider a Cartesian coordinate system, something like this, and okay. So, now we have this. So, what exactly are we going to do? Our first job is to rewrite the continuity equation which is now inhomogeneous and momentum equation which is homogeneous, and combine them to get one single inhomogeneous wave equation or rather the Helmholtz equation, I am sorry. So, the final form that we are looking at is del square operating upon plus k naught square operating upon p tilde, where p tilde is p function of x, y, z and e j omega t minus j rho naught q and some direct delta function. So, this is for a point source. So, how do we get to this form for these Cartesian system, Cartesian and circular cylindrical system? This is what we are going to study in this class. Well, so let us move ahead and we will define a coordinate system something like this. So, here we will have your say the z direction, this is your x, this is your y, okay, and what is the flux that what is the flux that enters in this phase. So, here we will have your rho u, and this is the let us say this is this direction, this length is delta x, delta y, delta z, and the flux that enters here is your velocity w, and the one that leaves here is also w, but we will look at the mass flux that leaves and goes inside and leaves from the other face and so on. So, let us just focus on your to begin with this particular face where which I am shading, this rectangular face. Net mass flux that enters this face is rho w at z, and the one that leaves, and of course, this is delta x, delta y, and one that leaves the other face is z plus delta z into delta x, delta y. Similarly, if you consider the face here, mass flux that goes here and leaves here, what is it that? So, delta delta y, delta z. So, this will have rho u term because this is the x direction. So, x and delta y, delta z, rho u at x plus delta x. So, plus this thing and the one that leaves on the y side is your delta z, delta x, rho v y. I mean this suffix means at y, and y plus delta y. Okay. So, this is the net mass flux that is created within the differential volume, mass flux that comes inside, leaves, comes inside and leaves, and so on, and this is equal to what? Plus all this while we were equating this thing to the net mass flux, the net temporal change of the mass flux of the mass inside this thing, that is your density times the volume. So, we have this particular guy sitting here. So, this is a small elemental volume in obviously in Cartesian coordinate system, delta x, delta y, delta z, and what we are going to do now is that all this while we were equating here. So, now of course, if we want to derive all this thing in circular cylindrical systems, things would be a bit more complicated in the sense that we need to transform from x, y, z to r, theta, z, and basically it essentially involves doing something to the Laplacian to get your del square by del x square terms and all those things, or else we can do these things from a from the continuity equation, momentum equation side of things as well. But for now we will stick to Cartesian coordinate system, and using that we will present one sort of a formulation. Now, what is happening here is that this is what we are getting all this while when there was no source inside this volume. Okay. However, if you consider a general source term inside this volume, let us say this entire thing has some sort of sources which inject mass or take out mass, and the distribution of such source is such that it is it is defined as, I am using a different color just to highlight this fact. So, let us say this is m mass, m as a function of t, which is distributed over the volume. So, this is delta x, delta y, delta z. So, why did we multiply here? This plus term of course is there because now we are assuming some sort of a term, and this m delta t is really the mass which is a function of time that is being injected or taken out of the system, or this elemental cube, and the m delta or m dot delta t basically tells you that this is per unit volume. So, you just have to multiply this to the entire differential volume or the small elemental volume to get the total mass that is being injected or taken out over the small elemental volume. Now, one thing we can straight away do here is that mass is nothing but density times say the volume velocity. So, basically this is q dot. So, the units of this is kg by meter cube, this is meter cube by this is kg by meter cube. You can consider this as flow rate. So, here you will have your kg meter cube, but this is again we are defining this as flow distribution per unit volume. So, this will have unit of per second only, and then you have this meter cube term. So, these things will get cancelled, and eventually what we will have is kg by second. So, that is the mass flow rate, and it is dimensionally consistent with this thing, because now you can clearly see here is kg by meter cube and meter cube. So, you will get kg, you will just get kg, and in the denominator you have del t, dou t. So, you get kg by second, and same thing one can verify for all the terms here. The point I am trying to make here is that this is dimensionally consistent rho q dot t and delta x, delta y, delta z. For special cases like if you have a thing like point source, then you would have terms like rho into rho q dot delta x, delta y, delta z, and suppose you have time varying source E j omega t, but it is localized at a point so we get this. Okay. So, this term would be something like this. So, for now this is just I am trying to get you a feel of this. So, what these direct delta function means. So, this is the first time I guess we are talking about these functions in this course. So, a small digression I must make. So, a direct delta function delta x is defined such that it is 0 for all values, or you can consider this as direct delta function in Cartesian system, and this is defined as 0 for all x not equal to x naught, and in the integral sense from minus infinity to infinity it comes out to be 1. So, that means that this is equal to a very very small quantity exactly at x is equal to x naught, where this guy is limit is tending to epsilon is tending to 0. So, this will kind of blow up. So, this is direct delta function is used in lot in engineering, while solving problems for engineering mechanics, structural mechanics, and basically representing some physical systems where you have point excitation or a point, you do something like you just have impulsive sound, something like if you do this. So, this is just like this is happening just at that instant of time. If you burst a balloon, so this is you then in such a case this direct delta function would be delta of t minus t naught. So, whatever force or whatever something whatever disturbance is happening, that is localized or that is acting at right at t is equal to t naught, and for all other values it is 0. So, mathematically it is defined like that, although it is tending to infinity at that instant in space, that instant in time I am sorry, or that particular point in space. In the overall sense it comes out to be finite, nice finite value. So, if you can have a beam something like this and you can have a force point load acting in this direction. So, this is modeled really by a direct delta function, force acting like this, or a point excitation is also there. So, in which case you will have this additional E j omega t term, meaning that there is an excitation force, harmonic excitation force, but localized, very very much localized in space at a single point. So, coming back to our discussion, we will keep this guy aside and move with a generality, and what we will do, we will go around doing our regular business, divide throughout by delta x, delta y, delta z, or probably take this guy common, delta x, delta y, delta z common on the right hand side, left hand side, and then take limit of delta x tending to 0, delta y tending to 0, delta z tending to 0, and when we do that we will, it is not a very great thing to see, I mean it is rather simple maths to see that in the limit of delta x tending to 0, delta y tending to 0, delta z tending to 0, what will happen is that you will have this is equal to this thing plus rho q delta t, delta x, delta y, delta z. I would do it something like this, is equal to, okay, rho naught is this is again taken common, and so this what we can do is that move this guy on the right hand side, actually write it something like this. Where this bold term means a vector, okay, or I would for now just for convenience sake what I am going to do is that write down the full blown form. And this is equal to rho q delta t, and I will take this guy also on the right hand side, and this is delta x, delta y, delta z is equal to 0. This is of course multiplied here. So, for this equation to hold for any generic volume, the term inside this thing must go to 0, because this you see this is a generic volume, delta x, delta y, delta z. In a big fluid you can consider a small volume, since since we are considering this volume to be arbitrary, this should hold for any delta x, delta y, delta z, that small dV volume, and for that this entire thing, the term inside must go to 0. So, what do we eventually get? We get rho q delta t. Okay. So, we get this guy. Okay. Continuity equation with the inhomogeneous volume source term sitting on the right hand side. Clearly, if q delta q dot t is 0, we get back our familiar homogeneous equation. So, that is the beauty of this formulation, it kind of reduces back to the homogeneous form in case there are no artificial or no sources within that volume. Now, clearly, if if you, like I was discussing a while back, if you have this term, only if you have a source term which is governed by given by this thing, if this particular form of q delta t is like this, then that means for a big volume, no matter how big it is, everywhere this q dot t is 0, only at a certain point in space x naught, y naught, z naught, this is non-zero, and in the integral sense it comes out to be finite. Okay. So, we get this sort of a thing. Now, what about the momentum equation? Momentum equation, there are no inhomogeneous terms on the right hand side. So, I would just sort of write it down like this, and actually before I even go to momentum equation, it is a good idea to actually kind of linearize the things, because we will be working in a linear formulation. So, rho is just your rho is nothing but rho naught plus rho tilde, and rho tilde is equal to p tilde by c naught square, from our isentropic equation of state. And let us consider a stationary medium, that is no mean flow. So, plus u naught, but u naught is not there, and this is v tilde omega, this is like this. So, under such conditions, this equation gets simplified to, I am directly writing down the steps without going into the details again, because it is something that we have sort of done before. So, we get this this is equal to and here we will get your rho naught, and let's say we have a point source representation. So, we will get this e j omega t sitting here. So, I would just say this is q dot t, and it is localized in space. So, x naught, y naught, and z naught. So, this is where the source is. Okay. What we could probably do here is that we can sort of insist on time harmonicity. So, we can put p e j omega t and those sort of terms, but before in fact we even do that, let us just box up this equation, meaning that this is an important result, let us say 1, we call it 1, and momentum equations, like I said, will remain the same, they are homogeneous. So, we get this similarly. And finally, rho naught into this thing is your. So, what we get is again taking a derivative with respect to the space here. So, idea is to eliminate the particle velocity components along each direction to get this. And what we do is that we will keep all this result aside and name these as equations 2, maybe a to c. Okay. And now take a time derivative of this equation, and that will set up the matters. So, once you do that, you will get, so this term will become rho naught into del t del x and here we have been insisting time harmonicity. So, I would put it this as E j omega t. So, here we get j omega q naught E j omega t minus this thing. So, we get this, and now if we substitute equations 2a to c back in here, okay, we will get we will get your Laplacian. Essentially, we are going to get the Laplacian. So, we will get this rho naught is also there here. So, let me just figure out. We will put this there are number of minus signs here. So, we get this Laplacian operating upon this, instead of each of these terms, this one, this one, this one, we put we take rho naught of course inside, and you will just get minus Laplacian times whatever you are getting, and this is equal to rho naught g. I would write this as j omega rho naught, j omega rho naught q naught okay, we will get this. Now, here of course del square means in Cartesian system, and we will soon see how do we get to the r theta system in a while. But before we do that, now let us sort of simplify these guys further. We will multiply, we will put this in the standard form, we multiply throughout by minus. So, we get this guy. So, this is the inhomogeneous wave equation, and you have this minus j omega rho naught q naught into x minus x naught, y minus y naught, z minus z naught, and mind you you have e j omega t sitting. Now, if we, so this is your inhomogeneous equation 3, you can say. Okay. So, this is what we are going to get. Now, if we assume that this is time harmonic, okay, so you will get your and e j omega t is taken out, we get this sort of a thing. Okay. And omega by c naught is k naught. So, that is your excitation wave number. The dimensions of that is per meter, or k naught square is 1/5 meter square. So, you eventually will get this term is j omega rho naught q naught into x minus x naught, y minus y naught, z minus z naught. Okay. So, this is a very important result. Now, this is your inhomogeneous in Cartesian coordinate system, inhomogeneous Helmholtz equation. Okay. So, there are lots of things we can do from here. The first thing that I would like to tell you, small digression here. So, you have to pay attention here. especially to this term that is sitting here. So, this again if you set q naught to 0, you get back our old friend homogeneous Helmholtz equation, in which case you get homogeneous, but we have inhomogeneous. So, we get this. What does it mean? It means that, like I said, the source is localized on the right at a particular point, but then what we are essentially trying to do, let us consider a rectangular chamber muffler, something like the inlet port is like this, and this is just a rough figure. This is something, you have a chamber something like this, and so you are trying to squeeze out the entire finite points into finite area into one point, this thing. So, as if the the entire thing is the inlet or the outlet ports are condensed down to a single point, the point of singularity, and that is what is represented by the Dirac delta function. So, they are basically the ports, the finite sized ports are represented by a point, mathematical point, finite sized or cross section area is represented by mathematical points in space, basically on the surface of the chamber. So, you can also later on to solve this thing, you can invoke the Kirchhoff-Helmholtz theorem, but we will probably not go into that detail now. We will just stick to this particular formulation and see how to use the solution of homogeneous equation to solve this. But before that, whatever solution we are going to get for this is called the Green's function solution. So, Green's function is by definition response to a point source in space or impulse happens in time, like I said, a clapping or bursting of a balloon. So, this is the Green's function representation of when you represent the piston by a point source. Now, of course, like I said, a much better representation at least of this thing is at least when you actually consider the complete span of the ports. Now, there are different theories that are used to characterize mufflers. The simplest one of course is the point source representation, which like assumes a finite size ports into points, like I said, but then you have theorems like methods like a uniform piston model. So, basically the finite port is still represented by finite thing only, but then over this entire cross section area the velocity or the pressure fronts are assumed to be uniform. That means to say, in other words, the next mathematically the more accurate model which we are going to use for doing some results and compare it with 3D simulations which were computed previously is uniform piston driven model, in which basically you tend to assume planar wave fronts in the port, planar wave fronts right at the chamber, right in chamber port interface. We assume it right from the start. Okay. So, this is one of the salient features of piston driven model, but it is much better than the Green's function, because now at least you are representing the ports by this thing, and we will soon see that you integrating the Green's functions over the port area can do a lot of good things for you. Here of course, there is modal coupling is not considered between the port and the chamber. That is one of the drawbacks of the piston driven model, but it still is much better than the Green's function or point source model, because of the fact that we are representing the ports, we are actually considering the finite size and considering some sort of an average representation of the variation of the port. So, we are kind of taking into account the pressure variations across the chamber over the surface area where the port is located, and using that to get the pressure response function of the impedance matrix parameters. And we will compare this with the the finite element results wherever they are available. And the next thing is basically your mode matching, which is perhaps the most accurate mode matching approach. mode matching. So, basically it considers coupling in this chamber and this chamber, and once you do that, then basically you tend to set up a set of equations and solve for the unknown coefficients, and eventually it can lead to either calculation of the 4 pole parameters, that is characterization of the system, or the computation of the transmission loss expressions, transmission loss thing. So, for but most of the automotive mufflers, typically which are less than D, less than 50 mm or something like that, this kind of thing is pretty much alright, because for the most of the frequencies of interest, the first higher order frequency in the circular ports will be at a much higher frequency. So, this would suffice for most of the automotive mufflers. For larger mufflers like industrial mufflers, you might have to consider mode matching. In fact, mode matching can be important for some quite a few popular muffler configurations like extend inlet and outlet systems. We will hopefully see that in the next week. Let us see how we go about it, but this is what it is. Now, let us go back to our previous slides where we have this kind of a thing. Now, we have Q naught like this, and then we have Q naught like this, but suppose let us have another representation which is your piston driven model. So, piston driven model, what are the changes that one needs to make? So, in such a system, you still have your rho into Q naught. I am not sorry, Q naught is basically velocity that is there. So, remember that units of Q naught were Q dot T were 1 by second, and this was kg by meter cube, and here it was meter cube. So, things were working out. So, so basically if we assume that the source is distributed uniformly over the port area and velocity is u naught, and we define a function such that over the face x y, let us say the port is located on the face x y at any generic point. So, f x y, this is equal to 1 over this port and 0 elsewhere, and in z dimension this is still this guy. So, and then of course, this the other terms pertaining to this thing will be delta y, delta x, this thing. So, what about the dimensionality of such things? Dimensionality wise, it should not be a problem. Okay, so kg by meter cube, and if we assume here by meter square, meter by second, and this is of course per meter, you have your direct delta function representation, and here you have your meter cube. So, under such a situation, this fxy, so this gets cancelled, I am sorry, these two gets cancelled, and this meter gets cancelled. So, fxy must be 1, which is basically your non-dimensional function. This is fxy is 1 over this area and 0 over the area shaded in green color. So, basically all we need to do for modeling the uniform piston driven model, which I have been telling you to be more accurate, is get use this, and of course, u naught is varying as e j omega t, and when we have such a kind of model, so in such a case we can work out the algebra instead of, if we have this rho q naught e j omega t and all that. So, what will happen? So, let us go to your this thing rho q naught. So, instead of let me write down, let me use another color. So, rho u naught e j omega t f x y direct delta function z minus z naught, and the other term. So, instead of this term, you will have this term in the bracket. So, as usual, you will have these things will be there. So, instead of this, we will have rho naught into u naught, and I would say like this f x y, something like this, and you will have this kind of a term. And so, now once we have this particular thing, what we will do is basically E j omega t is of course there. So, then let us do the other things. So, here you have rho naught j omega u naught E j omega t f x y direct delta z minus z naught like this. Okay. Instead of this thing we will have this. So, finally, what do we get? Let us get to the equation. So, instead of this thing we will have j omega rho naught u f of x y and direct delta z of z naught. Okay. So, this is your piston driven model representation. Now, coming back after this small digression, what we will do, for a rectangular chamber, let us say of something like this, you have things like this, this is let us say this is B H L, this is the x direction, y direction and z direction. For subject to the rigid wall boundary condition. So, at x is equal to 0 and b, we have dou x of this is 0. So, we have v is equal to 0 at x is equal to 0 and b, I am sorry, it is u, my mistake. Similarly, v and w are 0 at y is equal to 0 and h, and z is equal to 0 and L. So, the corresponding thing is y is 0, this is 0. Okay. Now, once we get that, I will leave some of the details for you to work. So, L is equal to 0 to infinity, m pi y by h this is the thing, and of course, you have your E j omega t. So, time harmonically it is behaving like this, and one thing that is there is nothing but L pi L by this square, m pi h by this square and n pi by b whole square. So, what we will do is that we will substitute, let us say equation 4 a b, where a corresponds to the point source representation and b corresponds to the piston driven representation. Okay. We will have this sort of a thing. Now, once we do that, we will substitute this guy back in equation 4 let us say a. Okay. We will substitute this guy in here and see what we get. So, obviously, this del square, if you operate say del square by del x square, if you operate upon say this term, you are going to get back cos, but with the minus sign. So, we will get minus m pi h whole square. Okay. So, you are going to get m pi sorry, this is not, I am sorry, n pi b. So, eventually what you will get is basically this thing n pi b So, we get this, and then you get your k square c l m n and all this cos functions. Okay, this summation is there, of course. This is a triple summation over L m n. So, I am not writing down this thing explicitly, but you have j omega rho naught q naught into direct delta functions. Okay. And you just get rid of the time term that is understood its time harmonic. So, here also there is e j omega t, and here also I am just, so it just cancels out, you just do not worry about it. Here we are stuck up with one important thing. What do? We have only, well, one equation and infinite constants. How many constants do we have? C, L, M, N. L varies from say 0, 1, 2, 3, 4 till infinity, and M also varies from 0, 1 to infinity, N also does so. So, technically we have infinite constants, but only one equation. So, how do we resolve this issue? How do we get these modal coefficients C, L, M, N? This is what we are after. These are modal coefficients, and unfortunately they are infinite of them, and we have unfortunately only one equation. So, how do we get calculate these values appropriately? So, had this been a in person class, I would have really expected one of you with lot of you would have decent background in engineering, maths, and related things. So, one of you would have actually come down to the board and worked it out, but given the online nature, I would probably give you the solution now. And so, we need to do something or invoke something called mode orthogonality. Okay. So, what we do? We should realize by now that cos of m pi m, let us say m, and this is well h, and cos of m1 pi y by h dy over 0 to h. This is equal to 0 if m is not equal to m1, and if m is equal to m1, then things are different. Okay. If m is equal to m1, then this is not 0, then it becomes cos square. So, you divide and multiply by 2, so it becomes 2 cos square. Okay. And then you invoke your cos 2 theta rule, and you will see that this will be half of h by 2. So, this is sufficient enough hint. This is not high school algebra or calculus or engineering math stuff. Things will become more complicated when you have Bessel functions. We are soon going to arrive at that. So, we will multiply this equation, let us say equation 5 with cos m1 pi h and n pi x by p. We will multiply both sides by this, multiply both sides. Okay. And then when we integrate, we multiply both sides and integrate. So, only we do integral, integrate over the volume. So, L h p. So, we get cos of m pi by h, cos of m1 pi h by y. We can pair this term similarly for x term, similarly for z term, dx dy dz. So, only when m is equal to m1, n is equal to n1, and L is equal to L1, only when you have such a thing it will survive. Okay. So, basically what we will get the modal coefficients. So, once we all the other modal coefficients will not survive, only C, L1, M1, N1 will survive, and we will have these integral values, which is we denote by N, L, M, N, and once we get this thing, we will substitute back in the solution that we get here to get the Green's function response. So, what I am going to do, instead of writing it up all together, I will present to you a paper that I published a few years back, and this is somewhere here. So, this was a paper on design of rectangular chambers published by another co-author. Also there was another co-author in this paper. This article appeared in Acoustics Australia in 2016. It has been some time now. So, we have this regular modal expansion business and natural frequencies of the rectangular box, and these are our integral values. So, this is 1 when m is equal to n is equal to L, and 0.5 for you can have a look at the different permutations, and this is the inhomogeneous point source equation, and we substitute as it said orthogonal modal solution of equation 2a for this one, that is basically this one, is substituted in equation 5 and using mode and evaluated using modal coefficients are evaluated using mode orthogonality of circular function, back substituted to obtain the Green's function representation for arbitrary location of ports. So, instead of naught or x naught, y naught, z naught, we have x s, y s, z s. We are basically the same thing. They represent the source coordinate, and r suffix represents the coordinates for the center of the receiver port. That is, where do you want to measure the function for a given excitation point source at x naught, y naught, z naught, or x s, y s, z s. So, this is the Green's function representation. Looks nasty, but it is not that nasty. It's a little bit of algebra and would get you there. So, this is the inhomogeneous solution of inhomogeneous point source equation. Okay. Clearly, when x r is equal to x s and all this r is equal to s, you have the source and receiver to be the same, and point source representation in such a thing is known to cause singularity problems. Okay. When you have so basically this is nothing but another thing that I want to tell you is that P, look at the units, P is the acoustic pressure and rho naught q naught is the mass velocity, kg by meter cube and meter cube by second. Okay. So, you get kg by second. So, mass velocity, acoustic mass velocity, pressure by acoustic mass velocity, that is your impedance. So, this is nothing but the impedance matrix parameter. So, once you get this, so for a 2 port system, if you have excitation at say one of the ports and measure the get the transfer function or get the the response function, then just by substituting r is equal to s, you can get z11 parameter. Similarly, by choosing another if you choose the receiver port to be the same as the outlet port, then you get the z21 parameters, and z12 is equal to z21. So, the moment you get z21, you know z12. Similarly, if you put r and s same for the other port which can be located anywhere, you get the source port, we get another response function. Okay. So, like this we can characterize in principle any number of system. I mean these things can be sort of anywhere, the number of ports as well as for we will concentrate only on a 2 port system. So, P is equal to Z matrix times V, where Z is Z11, Z21, Z12, Z22, the 2 cross 2 matrix. Now, like I have been mentioning, this point source representation not only is least accurate in terms of the underlying assumptions, the other issue is of course the singularity issue. So, people have like I have mentioned in this paper about the singularity issue published by Zhao and Kim. Now, you consider a piston driven model. So, which is the same thing what we derived a while back. This is 1 over the port area and 0 over the annular area. Now, what we do in order to get the solution of that, we notice that this function g, g is equal to rho naught q naught times j k naught c naught multiplied by this big expression is a solution of this thing. Okay. So, what we essentially do is that we substitute equation 6, that is Green's function solution, in equation number 5 by knowing that this is a solution. Okay. And then as I have mentioned, we have to go a little fast. So, what we do to get the solution is that we substitute this guy here and do the following mathematical operations. Once we do that, he will realize that Green's function, if we just integrate the Green's function over the port area and divide by this thing, we will get a solution, because you see this particular thing, this will be very comparable, this particular q naught, we are insisting that it is u naught into the port area. So, we are dividing this by, we are taking this s inside the integral sign, and u naught into f of x r y r. So, what's going to happen is that this particular thing will be highly comparable, or not highly comparable, will be exactly the same as this equation. So, if we, so this entire thing what I am sort of writing here, this is the solution, this particular thing, if we compare this entire equation here where I am pointing, this entire thing. So, this is the same as the equation shown here. So, if we were to just integrate the Green's function of the port area and divide it, we are going to get a solution by visual comparison, we can just sort of get it. So, Green's function, I mean it is not all useless work, it is actually quite useful, it is a good intermediate step to get the Green's function. So, and then we would also try to get the average response over the receiver port. So, that is why these formulations are there. I suggest you should probably try to download this paper on the internet, or else I can give it to you, and try to do the derivations by yourself and to learn further. So, this is how we get the general Z RS parameter for different locations of the receiver port on the XY phase, on the YZ phase, and on the Z X phase. So, once we do that, we get the impedance matrix parameters, and now we probably can develop some particular particular expressions for the integral when the port is located to get the definite integral. So, basically what it does is that in this paper exact the integrals were evaluated numerically using some Newton quadrature rules, more precisely Simpson's 3/8 rule, but the limits of integration where the ports is located xr minus rs is the radius of the port, and all these limits were carefully evaluated, and these things are there. So, basically one can characterize a rectangular chamber muffler. With this sort of a approach, one can characterize any number of port muffler, and we can sort of get the evaluate the transmission loss parameters once we get the impedance matrix parameter. So, this after that is regular stuff what we discussed in the first lecture of this week. And other thing that I want to quickly tell you is that let's consider the function, the influence of location of the port. So, this is something that you have to understand for particular cross section. So, cos say let us say m, this is x direction, this is y, m pi x by b. So, when m is equal to 0, this is cos of 0. So, this is just 1, that is a planar wave mode, or that is something that should come out very nicely, what we discussed while back. Now, when you have y is equal to 0, you are going to get this and all that. So, now you get the planar wave mode. Now, when m is equal to 1, you get cos pi x by b. When x is equal to b by 2, this is 0. So, you get a modal line here, and when y is equal to h by 2, you get a modal line. So, this is something that we discussed a long time back now, second week, the last couple of lectures or so. The point I am trying to make is that if the port is located at any point here, then m is equal to 1 mode can be suppressed, the first higher order mode along the x direction. Similarly, if it is located here, this mode can be suppressed, but if it is located somewhere here, 0 1 1 0 and 1 1 modes can be suppressed. Similarly, if the port is located at this point, it is easy to say this is 3 by 4 b, this is 3 h by 4 cos of 2 pi x by h. And so, if for such a function, when you have x is equal to 2 pi h by 3 h by 4. So, this is 0. Similarly, the mode, this particular mode can also be suppressed. So, basically in such a situation you have 0 2 2 0, 2 2 modes can be suppressed. So, one of the optimal configurations for a expansion chamber muffler can be something like this. Hopefully, we should be able to do some cases. One is at the center, the port is somewhere here, other can be a staggered one somewhere here at b by 4 L by 4 and that sort of a thing, or it can be also be located somewhere here for a reversal chamber kind of a configuration. And the other thing is your configuration, something like let me just open up the paper for you. So, other configuration that we did analyze, there are lots of configurations that we did analyze in this paper. So, how are we going to get a broadband transmission loss? So, I will probably show you some results, maybe run a couple of codes. And so, for a end inlet and a side outlet thing, we, if the side outlet port is located L by 2 along the z axis, we can nullify the first axial trough, and the location of the center of the port, at the center somewhere here at at x is equal to 0.5 b and y is equal to 0.5 h, 0 1 0 1 0 1 0 0 mode can be suppressed also. So, but then this is going to fail at the second axial resonance peak. Other configuration that we have is this side inlet and a side outlet port, and this is going to sort of do well until the 0 2 0 2 2 0 2 0 or 2 0 0 mode, at which frequency it is going to fail. Now, note that if for such a side inlet and a side outlet port, one of the ports is located at Z is equal to L by 4, other is located at L by 2, okay. And and on this face it is located at right at the midpoint of this thing, that is at y is equal to h by 2, and similarly here for this port it is located at b by 2, somewhere here. So basically what we get is is that for such a configuration, for a side inlet and side outlet configuration, if this is at 90 degrees, you can eliminate the plane wave will obviously fail, but you can sort of by cleverly locating the port not just at L by 4 and L by 2, but also ensuring a 90 degree angle between them, and this port being located at the center of the face, corresponding face, you can definitely eliminate the troughs, say by 011 or 101 mode, or these modes, and obviously 012 102 mode, and one can do a lot of interesting combinations, okay. So and then you have single and double outlet system. So what we are going to do in the next class is that we are going to derive in the next final couple of lectures for the next class, combined couple of lectures for the next class, we are going to kind of analyze a circular cylindrical muffler, okay, a circular cylindrical muffler with arbitrary location of inlet and outlet ports, and using a Green's function representation, and then integrating it to get the response to a piston driven model, and maybe do some algebra, and I will probably run some code for a circular chamber and show you some interesting results that we can get. So till that time, stay tuned, and I will see you very shortly. Thanks.